Okay. So let's look at this problem. So as I mentioned earlier, this is probably a combo problem. The previous problem is looking at the force P required to cause motion to lift B. We're turning it around and we want to find the horizontal force negative P to pull the wedge out. So I think the first thing we should do is draw our free body diagrams of the wedges. So I'll start here and I'll draw the upper wedge first. And let's see what's acting on that. Well, I have a 300-pound force acting vertically. And what else do I have? Well, the contact here at the wall, there would be a normal force. So I'll call that the normal force at D. Now, if I pull the wedge out to the left, block B is going to move up or down? It's going to move down, so the friction force will be opposite. It'll be up. Then I'll have a normal force. I don't know what I'll call that. I'll just call it N1. Now, if you don't see this next part, I'm going to skip over and draw the free body diagram of the bottom wedge. This might be a little easier for you to see. If you get confused, definitely put in what you know. So remember, our force P is to the left, negative P, right? So motion is to the left, so friction forces will be to the right. So if it's to the right here, it's to the left, equal and opposite there. So I'll just call this the friction at B. And then this would be the normal force, which I call N1. And then at C, you'd have a normal force, call it N2. And again, since the wedge is moving to the left, the friction force would be to the right. And does block A weigh anything? Neither of the blocks weigh anything. There's just a 300-pound force on the top of block B. So this is block B. This is block A. So I'll just call this free body diagram 1 and free body diagram 2. So now we just need to look at them and see what we know and come up with a strategy. Now, since we know the block is moving to the left, we also have our friction relationships here. So really, on this block 2, our unknowns would be N1, then we know the friction, N2, then we know this friction, and P. So I have 3 unknowns, N1, N2, N2. P. If I go to free body diagram 1, what do I have? Again, the block is going to move down, so I have a relationship here, so there's just one unknown, the normal force. Same relationship here because of movement, impending movement, so I just don't know the normal force. So really, free body diagram 1 just has 2 unknowns, N1 and ND. So that's where I'll start. I'll start with free body 1. What makes this a little challenging is you'll notice that both the normal force and the friction force have components in both directions. And just to remind you, that's 15 degrees and 15 degrees. So let's start. We'll sum forces in the x direction and see what we get. So in the x direction, I would have the normal force at D, and I'd have the x component of the friction force at B, and that would be cosine of 15. And I would have the horizontal component of the normal force, and that's to the right, so that's positive. That would be N1 sine 15. That doesn't look too exciting right now. That's some forces in the y direction. So let's see what we've got. We've got 300 pounds acting down. Got the friction force at D going up.
It's 3,000.
Oh, it's 3,000. Thank you. Let's see. I'll just have to scratch that out. I got no room to put an extra 0. Thank you. I may be able to squeeze one in there. Doesn't look very good. I wish they'd use comma separators. I see thousands better with comma separators. This is a personal thing. Okay, so I got 3,000 acting down, friction force is up, and then I have both these components acting up. So the friction component would be positive, and that would be the friction at B times the sine of 15. And then the normal component is also acting up, and that would be cosine 15. At first, that doesn't look very exciting. But remember that the friction force at D is related to the normal force at D, because we have that additional equation. And also we know that the friction force at B is related to the normal force at 1. So if we take our time, we should be able to solve this. Let's see. Put everything in terms of normal force. I'll take a shot at this. I'll call this equation 1, equation 2, 3, and 4. So if I rewrite 1, I'm going to take equation 1, I'm going to put force B in there. I should get a relationship between normal D and normal 1. So let's see if I can do that. So I've got normal at D minus mu B N1 cosine 15 plus N1 sine 15. And that should be equal to 0. So that means I can say that ND is going to be equal to all that stuff. At this point, I could factor out the N1, and I would have sine 15 minus mu B cosine 15. And you guys can calculate that and actually get a number. Let's see what that's going to be. 15 cosine. The coefficient of friction at B is 0.1. AC and BD, let's see, AC and BD is, okay, yeah, 0.1.
Yeah, 0.162 for the parentheses.
So you're, oh, I'm sorry. Hang on, I was halfway through that. What did you get for this number?
0.162.
Oh, I did it backwards. Sorry. That's what I got. So I got N1 times 0.162. So I can now take that and plug that in where? To equation 2. So I'll go back to blue 2. Let's see what I've got. Got 3,000. I've got FD. What's FD? That's these two things. So let's see, I'll start with FD. So FD is mu D times the normal at D. The normal at D is this, N1.162. So that term is FD, plus the friction force at B, which is this, which is mu B N1 times sine 15. And then I finally got the N plus N1 cosine 15. And then I forgot, there's my 3,000. So this whole thing is equal to 3,000. So a little bit of work, but I got everything in terms of N1. So I should be able to solve for N1. Can I do that in a timely manner? I am not sure. Let's see. See if I can pull this off. Okay. So what's mu D? That is this surface, which is AC, and AC is 0.2, right? So 0.2, 0.167 times. Mu B, that's the AB surface, which is 0.1. 15 sine times plus 15 cosine. I got 2,929 when I solve for N1. I just calculated all these coefficients, added them together, and then divided both sides by that. I think that looks reasonable. So once I have N1, then
You can find ND.
I can find ND. So I just take that value times 0.162.
I have the same value.
Oh, great. So 474.5 pounds for ND. And now that I've got all that, believe it or not, I'm ready to roll. A lot of work, and we're only halfway through, right? Because now we need to go to free body diagram 2 and apply N1 and solve for everybody else. I think it won't be as bad as it seems, though. I don't think I have enough room on this piece of paper, so let me get another piece. And I'll just slide it over here. And we'll work those equations there. So now going to free body diagram 2. Right? Remember now I've just solved for N1 and in that sense also the friction force. So you can see I just have 3 unknowns. Now I'm just trying to get P. So how can I get P quickly?
Summation.
Yeah, if I sum forces in the x, see, I'm going to have to get this friction force, and to get the friction force, I'm going to have the normal force. So it looks like we need to sum forces in the y direction first. So if we sum forces in the y direction, set it equal to 0, what do I have? I have N2 acting up, and then the y component of N1 acting down, so that'd be minus N1 cosine 15, and then the vertical component of the friction, which is also acting down, which would be the friction at B times the sine of 15. Now, recall that the friction at B is the surface there times normal 1. So I know that. Remember, I know N1. So I should be able to solve for N2. It should be N1. What do we solve for N1 as?
It's 2,929.
Yeah, so that'll be 2,929. That's N1. Cosine 15 minus this, which is mu B. That's the difference between the two wedges, which is 0.1 times the same normal force, 2,929, times sine 15. So whatever that is.
$2,905.
2,000 what?
905.
Okay. 2,905, and that's pounds. So that's N2. So finally, we can sum forces in the x direction and find our value of P. So if P acting to the left, that's minus P. And then all the forces that have x components. So it'll be the force at C plus the horizontal component of the friction force at B. That'll be cosine 15. And then the normal force is to the right. So that'll be normal 1 sine 15. So P is going to be equal to all that. So what's FC? FC will be mu at that point times N2, and mu at AC is 0.2 times 2905. That's the friction force F. The friction force at B is mu B N1, which is coefficient of friction of 0.1 times 2929 pounds. And that's times the cosine of 15. And then minus N1, which is 2929 pounds, times sine of 15. That's a lot of work. So what's P equal to?
105.8.
105.8. Sounds reasonable to me. Now, let's take a breath here and discuss this. 1. Is this a problem you can do on the exam? No. Unless I gave you the whole hour to do it. So I don't think I'm going to do that. The interesting thing here is that when we first started, it's a pretty innocent looking problem. So wedges give you that extra difficulty in that the normal and the friction forces are at some angle, which means they both have x and y components. And that's why you'll notice our equations can get a little complicated. So again, this is a good problem for homework and also for instruction, but really not one to be too concerned about. Now I can make this problem a lot easier by this incline would not be a wedge, it would just be a block. And then the angles would make it a far simpler problem. I've been working on it here for about, see how long the video's been running, 20 minutes. So really not really a good test problem.